Hello, good morning everyone. Is this audible? Hello, good morning everyone. Is this audible? So, am I audible? Please join. If I am audible, please join. Okay. Okay, Shogoto, Shorupo, yes. Yes, good morning. Okay, please join. Please join. Ushoshi, good morning. Good morning, everybody. Ankon, good morning. So, first, I discuss a theorem the statement of the theorem is Shubhrojit, this is not a Bengali class. Please don't write this type of thing. Thank you. Let capital A be a matrix where good morning Shohini, where the k roots lambda 1, lambda 2, lambda k of its where the k roots lambda 1, lambda 2, lambda k of it are distinct, that is lambda 1 not equal to lambda 2, lambda k, then the vector x1 curl, x2 curl, xk curl corresponding to lambda 1, lambda 2, lambda k are necessarily, this is a characteristic vector, necessarily independent. Proof. Let, if possible, x1 curl, x2 curl, xk curl be dependent vectors, then we know there exists at J such that xj can be written as a linear combination of previous vector x1, x2, xj minus 1. We know this result. So let J be the smallest integer such that x1 curl, x2 curl, x j curl are dependent. This means xj curl can be written as a linear combination of x1, x2, xj minus 1 curl. That is, there exists constant beta 1, beta 2, beta j minus 1 such that xj curl equal to beta 1 x1 curl, beta 2 x2 curl, beta j minus 1 xj minus 1 curl. Now pre-multiplying a both sides, then we get since xj curl is a characteristic vector corresponding characteristic root lambda j, so this gives lambda j xj curl beta 1 lambda 1 x1 curl, beta 2 lambda 2 x2 curl, beta j minus 1 lambda j minus 1 xj minus 1 curl, suppose lambda j equal to 0, then from 1, I denote this by 1, we have beta 1 lambda 1 x1 curve, beta 2 lambda 2 x2 curve, beta j minus 1 lambda j minus 1 xj minus 1 curve, equal to 0 curve. I denote this by 2. Since x1, x2, xj minus 1 be a set of independent vectors, this is from these assumptions. Since we assume that let j be the smallest integer such that x1, x2, xj are dependent, that means x1, x2, xj minus 1 is a set of independent vector. Hence this is a set of independent vector. This implies beta 1 lambda 1 equal to 0, beta 2 lambda 2 equal to 0, beta j minus 1 lambda j minus 1 equal to 0. Since we assume that lambda j 0, this implies, see, we assume that we state the theorem as A be a matrix where k roots lambda 1, lambda 2, lambda k of it of A are all distinct, lambda 1, lambda 2, lambda k not equal to 0. So this is the assumptions of the roots of A. So if lambda j is 0, then since all roots are distinct, so this implies lambda 1 not equal to 0, lambda 2 not equal to 0, lambda j minus 1 not equal to 0. Clear? Please tell me. Please tell me, is this clear or not? Can I repeat it again? See, we assume that the roots of A, according to the statement of this theorem, the roots of A are all distinct. If lambda j is 0, since all root distinct, if lambda j is 0, this means lambda 1 to lambda j minus 1 all are non-zero, because lambda j is 0 and all roots are distinct. This implies lambda 1 to lambda j minus 1 are non-zero. Hence beta 1 equal to 0, beta 2 equal to 0, beta j minus 1 equal to 0. Clear? So from star xj curve equal to 0, which is impossible. because why this is impossible? Because xj car is an eigenvalue, eigenvector. So it should be non-null vector. Therefore, this assumption lambda j equal to 0 is wrong. So lambda j should be non-zero. So lambda j non-zero means from 1 xj car x1 car xj minus 1 car. Okay. Denote this by 3. Again from star and 3, if we compare the coefficient, then we see that beta 1 equal to lambda 1 by lambda j, beta 1, this means lambda 1 equal to lambda j. Similarly, beta 2 equal to beta 2 lambda 2 lambda j, this means lambda 2 equal to lambda j. And so on. Hence, lambda 1, lambda 2, lambda j all are equal. But this is impossible because we assume that all lambdas are all distinct. So, but as lambda 1 not equal to lambda 2 not equal to lambda j, then the above relations means this. Hold if and only if beta 1, beta 2, beta j minus 1 should be 0. So the assumptions, this is impossible, because if this thing is hold, this implies xj current 0 current from start, which is again impossible because xj is a which is impossible as xj current is a non-null vector because is a eigenvector, being an eigenvector. So therefore the assumptions that is the assumption that xj curve belonging to spanning set of belonging to the linear span of xj minus 1, that is xj curve written as a linear combination of x to x1 x2 xj minus 1 is not true. Therefore x1 xj is an independent set, and since this j varies from 2 to k, so this means x1 xk is an set of linearly independent vector. Hence proved. So please tell me if you have any doubt. Please tell me if you have any doubt. Shashwati, Sohini, Sarupo, Ushoshi, Topomoi, please tell me. Is it clear? If so, can I rub this portion? Okay, Sarupa. Okay, Subhajit, thank you. Next theorem, the characteristic roots roots of a real symmetric matrix are always real and the characteristic vector of them can always be chosen to be real. So this is your homework, please prove yourself. And the last theorem of this chapter, that is let lambda and mu be two distinct roots of distinct real root of real symmetric matrix A, and let x curl and y curl the characteristic vectors of A corresponding to lambda and mu respectively, then x is orthogonal to y curl. So please prove yourself. This is another homework. So this is all about this chapter, eigenvalue and eigenvector. Now I discuss some portion of quadratic form. The definition of quadratic form, we know this whole thing in our undergraduate level. However, I discuss mainly here the canonical reduction of quadratic form. So, before discussing the canonical reduction of quadratic form, I like to define definition of quadratic form. An expression of the type sum over I from 1 to n, sum over j from 1 to n aij xi xj, where aij are constant coefficient where xi xj are variable is called a quadratic form. With respect to variables x1, x2, xn, it is denoted by qx curl. This we can represent this by x curl. X curl is a vector of Rn which components are x1, x2, xn. And this expression can be written as this, where A equal to A is a square matrix of order n cross n whose ijth element is aij. You know all this. Now the classification of a quadratic form we know if qx curl, that means x curl prime ax curl greater than 0 for all x curl non-null x curl and 0 if and only if x curl equal to 0 curl. This means qx curl here I consider only R Swarupo, real number. Okay. So Qx is a positive definite quadratic form and the corresponding matrix A is called positive definite matrix. not call, is a positive definite matrix. Is a positive definite matrix. This A matrix has a name. This A matrix is called matrix of a quadratic form. Of the quadratic form. Okay. And this qx curl, x curl prime x curl greater than equal to 0 for all x curl and equal to 0 for some x curl not equal to 0. This implies qx curl is positive semi-definite quadratic form and corresponding matrix A is a positive semi-definite quadratic, positive semi-definite matrix. Okay. Similarly, we define if qx curl x curl A x curl less than 0 for all x curl not equal to 0 curl and equal to 0 if and only if x curl equal to 0 curl. This is called positive negative definite matrix, a negative definite quadratic form, and corresponding matrix A is called A is a negative definite matrix. Similarly, if this qx less than equal to 0 for all x curl and equal to 0 for some x curl not equal to 0 curl, then this qx curl is called negative semi-definite quadratic form and corresponding matrix A is a negative semi-definite matrix. And otherwise qx is a indefinite matrix. That means for at least one x curl not equal to 0, x curl A x curl greater than equal to 0, another x curl greater than 0, another x curl it should be less than equal to 0, then it is a negative indefinite quadratic form. And you know all this, I think you knew all this definition in undergraduate level, so I just briefly tell this thing. And one thing we know, we can always choose a matrix A as a symmetric matrix. I think you know the proof. The proof is very simple. Suppose your quadratic form qx curl x curl prime A x curl where A is not symmetric matrix, and its element is ijth element is aij. Now take B, whose element is bij, ijth element, where bij computed as constructed as aij plus aji by 2, then you easily check that B transpose equal to B. Now x curl prime B x curl equal to x curl prime A plus A transpose by 2 x curl. So this is same as Ax, x curl prime Ax curl. Hence we can always choose matrix A as a symmetric matrix. Before discussing the canonical reduction, I want to define elementary operations. I already mentioned that in my previous class, elementary operation is nothing but a pre and post multiplied by some non-singular matrix which are called elementary matrix. So first I define elementary operation. First operation is, I denote this by U1. This means multiplying a row or a column by a scalar C. This operation means if you pre-multiply by a matrix delta whose ijth element delta ij, where delta rr, suppose I apply this operation on rth row. I will discuss this with an example. Please let me finish it first. Delta rr equal to C. This is a chronicle delta. Chronicle delta means delta ij, delta rr equal to C, delta ii equal to 1 if I not equal to r, and delta ij equal to 0. So consider the matrix A like that, 1 2 0. Okay, Sharnabu, thank you. I think you, okay. E1, this is E1. Is it now visible, Sharnabu? Is it visible now? Sharnav, can you? Okay, Sharupu. Yes. Okay, thank you, Sharnav. So, suppose okay. A is a matrix. I take A is a 3 cross 3 matrix whose elements are A11, A12, A13, A21, A22, A23, A31, A32, A33, and I want to multiply second row of a matrix by C. This is the operation. And then this thing should be okay. So now my claim is for this operation, if our delta is here, R is 2, so it should be and mind it, this C should be non-zero. Okay, so now you multiply delta A, then you get this matrix. And if you multiply second column of A, so then Sarpo, which portion you want to say? Can I repeat the operation you want? Okay. See, E1, I define E1 operation means row or column, left matrix. Left matrix means this delta. Okay. Okay, delta means, see, delta delta define as, in generally, if you apply this operation on rth row, rth row, that means if you multiply matrix rth row of matrix A by a constant C, then this is nothing but a pre-multiplication by a non-singular matrix delta, where delta defined as whose diagonal elements all 1 except rth diagonal element, and rth diagonal element is C, and others of diagonal elements are 0. Off diagonal elements are 0. So in that way we define delta. If we multiply delta with A, then you get the matrix which is nothing but, if you multiply the rth row of a matrix A by C, these two matrices are same. For this I illustrate this by this example. Suppose your matrix A is this is a 3 cross 3 matrix. Okay, if you want to multiply second row, this second row by C, then you get this. So this operation nothing but a, if your delta defined is as follow 1 0 0 0 0 0 0 1, just as, because here R is 2, in this case R is 2, so second R is 2, that means delta 2 2 should be C, and delta 1 1, delta 3 3 here 0, 1, and other off diagonal elements are 0. In that case, if you pre-multiply pre-multiply A by delta, then you get this matrix. Okay, so you can check, if you want to multiply, instead of second row, if you want to multiply third row, then your delta is and if you want to multiply first row, by C, then your delta is okay. Clear, Sharupo? Sharupo, clear? This is a non-singular transformation. Okay, because A is a non-singular matrix, one-to-one transformation. Okay, Shubhrojit. Okay, so, and if you apply these on row, suppose if you want apply this on column, so that is C into C2, so we just post multiply A by delta, where delta is, in that case your delta is 0 0 0 C 0 0 0 1 and so on. So this E1 operation, that is multiplying row or column by scalar C, is nothing but a pre-multiply. When you use row operation, pre-multiply by a elementary matrix delta, or when you apply column operation, this is a post multiply by a elementary matrix delta. And since this delta is a non-singular matrix, hence the rank of a matrix is unchanged, because we know if you pre-multiply or post multiply by a non-singular matrix, your original rank of original matrix is unchanged. So now next, E2 operation, replacing the rth row or column by the rth row column plus lambda into the sth row or column. So here delta here I use a matrix ERS because I apply replace rth row, these are by rth row plus lambda into sth row. So in this operation rth and sth row are involved, so I denote this matrix by rs and within bracket lambda is constant. So this matrix, suppose its element is Eij and the Eij as whose diagonal element Ei equal to 1 for all I and only one non-diagonal element are non-zero, that is ERS, which is equal to lambda, and Eij equal to 0 otherwise. So I illustrate this by an example. Suppose your matrix, I consider 3 cross 3 matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. Now you change the second row, that means r equal to 2 here, by second row plus 3 lambda or 3 by first row. So r2s is equal to 1. Clear? So then you get a matrix sorry, this is 3 and 3-1, 3-2, 3-3. So here your ERS means E21, lambda means 3 is equal to all diagonal elements are 1 and E21 means this is 3, others element are 0. So if you pre-multiply A by this matrix, you get this matrix. So is it okay? If you have any doubt, please tell me. Up to that, please tell me. Subhrojit, Swarupo, tell me if you have any doubt. Okay, Subhrojit, okay, Disha. So similarly, you can define other operations, such type of operations. If you apply the row operation, then you pre-multiply, and if you apply this, okay, thank you Shoini. If you apply this on column, suppose if you change the second column by this is nothing but a post multiplied. In that case, post multiplied by this matrix E2 1 3. Okay, now the last operations, that is E3, interchanging two rows, or columns. So this is nothing but a pre-multiplication. If you apply row, if you interchange two rows, this is nothing but a pre-multiplication of pre-multiplying of pre-multiplying of successively by matrices E is R minus 1 E RS 1 ESR minus 1, then delta. So suppose you interchange Rth and Sth row, so this is nothing but a pre-multiplying by these matrices successively. For example, if you consider 3 cross 3 matrix A whose elements are this, and suppose if you interchange first row and second row of a matrix, and in that case you get this. So this is, so here your R is 1, S is 2, so you just So this matrix gives this. So these three type of operation we use, and we see that this three type of operation is nothing but a pre-multiplication and post-multiplication by a non-singular matrix. Hence the rank of this matrix is unchanged. So for canonical reduction, we use these elementary operations, three elementary operations, E1, E2, E3. So first I consider I think it is better to illustrate by an example. Suppose Ux squared is equal to 5x1 square x2 square plus 10 z1 square minus 4 x3 square 4 x2 x3 10 x1 x3. Okay, suppose I consider this quadratic form, and our problem is to reduce this qx to a canonical form. The definition of canonical reduction of a quadratic form is let A be a positive definite matrix, then x curl prime ax curl ux curl greater than 0 for all x curl not equal to 0, we know it. Then we transform qx curl to uy curl, y curl prime delta y curl is equal to I from 1 to n lambda I yi square so this is the canonical form. If this means if by any real non-singular linear transformation, Subhrojit asked me what type of transformation used here. All are non-singular transformation. I already answered his question or queries. Non-singular linear transformation, a real quadratic form be expressed as a sum of as a sum and difference of the squares of the new variable then this latter expression is called the canonical form of the given form. So this is the example. If A is positive definite matrix, then after some non-singular transformation we can get Qy curve which gives sum over I from 1 to n lambda yi square. Because here I consider A is a positive definite, so this means all eigenvalues greater than 0. You knew this thing in undergraduate level. So this means this should be, this quadratic form Qx curve can be expressed as a sum of squares of a new variable y1, y2, yn, and if it is negative definite, then all lambda should be less than 0. If it is indefinite, some lambda is greater than 0, some lambdas are less than 0, and if it is positive semi-definite, then you get some lambda greater than 0, the number of lambdas which are greater than 0 should be less than n, okay, and so on. So this is the definition. Actually the canonical reduction is nothing but a convert this Qx curve to y curve, Qy curve, such that sum over Qy curve is lambda I, not necessarily eigenvector, eigenvalue. You can convert this also Qy curve as Qy curve sum over I from 1 to 3 lambda yi square, or you can convert this normalized form also yi square. This is a normalized form whose coefficients are all 1s, otherwise this is a canonical reduction. Okay, now the problem is convert this to canonical reduction or normalized form. Normalized form also a canonical form. Okay, so we know we can always choose matrix A symmetric matrix. So here A is, the diagonal elements are this, okay, and this is the, just write it like that, x1, x2, x3, x1, x2, x3. So x1 square, the coefficient of x1 square is 5. This is a coefficient matrix. Then x1, x2, a coefficient of x1, x2 is 0. Then x1, x3, this is 4 in total. So distributed it as follow: -2, -2, then you get -4. Similarly, sorry, this is -5, -5, because x1, x3, coefficient of x1, x3 is -10. and this is minus 4, so this is minus 2, minus 2. Okay, so this is your matrix A. Now I convert this matrix to a diagonal matrix, so this is minus 5. So first I apply the operation R3 R1 plus R3, so this gives and here the matrix P1, I denote this by P1, it is, I denote this matrix by ERS. Here R is 3, S is 1 and lambda is 1. Okay, clear? That means now mind it, here we simultaneously apply row and column operation. First apply row operation, then same operation apply on columns, that is C3 C1 plus C3 and here if you pre-multiply it E31 by this matrix, sorry, it is E1 column operation, that means transpose of this matrix, transpose of this matrix. So that means you post multiply it by this matrix, okay. Now similarly R3 so this is E32 2 and then apply same operation on column, this is a transpose of this matrix. So now to get the canonical form, and where y1, so see that you just multiply first you 311 a E311 transpose, then you apply E322 E322 transpose. So this is the operation, whole operation. E32, okay. Oh, is it 1? Okay. Well, this is silly mistake. Now it is okay. Disha, Dishadi, Ankon. So this is the operation. And thank you. So okay, Ankon, please ignore. Okay. Thank you. X-card. So you see that this is our y card. This is our y card. This is a y card. So y card is so if you multiply all these things, then you can get y1, y2, y3. So new variable comes from this relation. Okay, so this is called canonical reduction, and if you want to make it normalized form, then you need another two transformation. mind it, you need to apply row and column simultaneously. So instead of 5 you use here root 5, because you need to apply column of same column operation on same column. So this is a normalized form, and from this it is clear that this is a positive definite quadratic form, because all diagonal elements of this matrix are greater than 0. And if you get this normalized form, you need 2 more linear transformation. This for delta, first, so delta is 1 by root over 5 0 0 0 1 0 0 0 1, and you need to add this thing here. So for normalized form you get a new variable y1 y2 y3 from this relationship. Okay, so this is this canonical reduction and normalized form. You can get in that way canonical form or normalized form, and you can think it in other way also. Suppose you know this thing. Okay, Shubhrajit says the inverse. Yes, Shubhrajit, you are right. Thank you. Thank you, thank you, thank you. This x curl should be y curl, and just this is okay. Thank you. Yes, 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 yes. Actually, okay. So this gives us x curl A. I tell. Thank you. You rightly pointed out this thing. X curl prime. Then you get this matrix and y curl prime. This matrix, I denote this matrix by B y curl, where B equal to okay. So this is that. Okay. So now if this thing is x curl, then x curl is nothing but a and take this is as a P matrix, P obviously non-singular matrix, then y curl should be P inverse x curl. Thank you, Shuprojit. So this is the derivation. Okay, so first you multiply these two matrices and denote this by P, and it should be x1, x2, x3. So denote these matrices by P. This P x curl equal to y curl. So x curl should be P inverse y curl. Okay. Clear? Thank you, Shubhrojit. You rightly pointed out. Actually, this is my mistake. Sorry. Have you any problem? Anybody please tell me up to that derivations. Can I expand more? Need the explanation more? Please tell me. Take your time. Please tell me if need more explanation. I have no problem. So please tell me, except Shubhrojit, please tell me if you have any doubt. Just raise this thing, then you can easily see that this is nothing but a P x curl equal to y curl, and the y curl is x curl is P inverse y curl. Oh, sorry. So this is y1, y2, y3. Okay. Please correct this thing. P y curl equal to x curl. This implies y curl equal to P inverse x curl. Thank you. Another way you can think this. Let lambda 1, lambda 2, lambda r be eigenvalues of a matrix A, and x1 curl, x2 curl, xi1 curl, xi2 curl, xi r curl be orthonormal eigenvector corresponding So please tell me, except Sharupo Subhrojit, is there any problem? Are you face any difficulties regarding this calculation? Please tell me. Can I proceed? Bishari, Shohini, Vishwanath, Paramita, Ruchira, Shashwati, please tell me. Disha, tell me. Okay, Shohini says no doubt. I am happy if you tell me that I have a doubt. Okay, thank you. So next let lambda 1, lambda 2, lambda be eigenvalues of A, and xi1, xi2, xi be orthonormal eigenvectors corresponding eigenvalue lambda 1, lambda 2, lambda r. Then PAP, we know this thing. Suppose A is not a full rank matrix and rank of A is R, where P is, we know this thing, this is from spectral decomposition. This matrix I think it is better if I not necessarily maybe 0 may not be 0, whatever that, but we can always get okay non-null eigenvectors, and these are orthonormal eigenvectors. So now see that so if you take, so here Px curl equal to y curl, because this is a all independent vector, so this should be this. So in that way we can get this transformation, and in that way we can convert any quadratic form to its canonical form. And if all lambdas are 0, we know then this is called a positive definite quadratic form. If some lambda is greater than 0 and other are 0, then it is called positive semi-definite. And if some lambda is greater than 0 and some lambda is less than 0, then it is called indefinite. If all lambda is less than 0, then it is called negative definite. If some lambda less than 0 and some lambda lambda is at 0, then it is called negative semi-definite. Actually, the why this thing is needed, because if you reduce any quadratic form to a canonical form, then easily you classify the quadratic form whether it is positive definite, positive semi-definite, negative definite, indefinite, semi-negative definite. Otherwise, from the quadratic a general quadratic form, that is x curl prime ax curl, you cannot classify this quadratic form. For classification of quadratic form, you need to reduce quadratic form to its canonical form. Okay, this is all about canonical form. And from this thing, if A is positive definite matrix, then all lambda is greater than 0, and we denote this diagonal matrix by lambda. Since all because A is positive definite, then all lambda is greater than 0, so we write capital lambda equal to by lambda half into lambda half, and these matrix are non-singular, so A inverse and we denote this by B prime. Hence, any non-singular matrix can be written as any positive definite matrix can be written as a product of two non-singular matrices. We know this result. Now the last portion is Chronicle product. Let A be a matrix of order m cross n, whose ijth element is Aij, and B be a matrix whose order P cross Q, whose ijth element is Bij, then chronicle product of A and B defined as A This is the chronicle product symbol. Is an which is an MP cross NQ matrix. This is product. Is it visible? Product. Okay. So matrix expressible as a partition matrix with aijb as the ijth partition, I from 1 to n and j from 1 to n. Example, suppose your A matrix like that, not necessarily square matrix, here I consider a rectangular matrix of order 2 cross 3 and another matrix B, here I consider order of a B matrix is 3 cross 2, then A chronicle B so this is need to take more space, so I erased this portion first. So the matrix this equal to third column is just multiplied A12 B11 A12 B21 A12 B31 A21 B11 sorry A22 B21 A22 B2 3 then fourth column A12 B12 A12 B13 sorry 22 A12 B31 A22 B12 A22 B22 B31 and this is a fifth column A13 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 A23 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 and sixth column so this is a first column, second column, third column, fourth column, fifth column and sixth column and the row is 6. So the order of this matrix here is 6 cross 6. This is the example of chronicle product. In that way we can get the chronicle product of a matrix. This is again a matrix but its order is MP cross NQ. Okay, so this is your homework. You can easily check the following property of chronicle product. Zero in chronicle product, 0 is a matrix or matrix, null matrix. This gives null matrix. You can check this property. If we are two scalar, okay, A1 A2 two matrices. This is a matrix multiplication A1 A2. Again get a matrix B1 B2, two other matrices, the simple matrix multiplication. So this is nothing but a provided inverses exist. Using any G inverse, this transpose so please check this thing. These are also homework. So please tell me if you have any doubt regarding this chronicle product. Otherwise I want to end the stream. This is all about your linear algebra portions. If you need more topic regarding this linear algebra, or you need more discussion regarding this linear algebra, please write to our channel. Then we will definitely address your queries and maybe take or arrange a class. Okay, so please tell me if you have any problem. Swarupa say no doubt. So what about other? Please tell me. So can I say thank you and end the? Can I end the stream now? Please tell me. Okay, Disha, thank you. So if you have any doubt, any queries, please let me. Please tell us. Then we can definitely arrange a class regarding this on this topic, linear algebra. So this is all about the linear algebra. This is mainly based on MSc statistics students. So hopefully you enjoy the classes. That this is the 12th number class. Okay. So can I close the in the stream. Thank you, thank you. I think everybody. Okay, Shoini, Shashwati, thank you everybody. So I want to end the stream now. So thank you.